Hello students, let's start today with ionic equilibrium. And before we deal with ionic equilibrium, I would like to deal with an electrolyte first. So an electrolyte is defined as a compound whose aqueous solution or melt conducts electricity. On the other hand, a compound whose aqueous solution or melt does not conduct electricity is called a non-electrolyte. So we'll see about strong and weak electrolytes. Before that, you should know about degree of dissociation. The fraction of the total number of molecules which dissociates into ions is called the degree of ionization or degree of dissociation and is usually represented by alpha. That is, alpha equals to number of moles dissociated upon total number of moles taken. So alpha is the degree of dissociation there. Next we come to a strong electrolyte. A strong electrolyte is defined as a substance which dissociates almost completely into ions in aqueous solution and hence is a very good conductor of electricity. So all those substances that dissociates almost completely into ions in aqueous solution. Example, sodium hydroxide, potassium hydroxide, HCl, H2SO4, etc. A weak electrolyte is defined as a substance which dissociates to a small extent in aqueous solution and hence conducts electricity also to a small extent. Example, NH4OH, CH3COOH, etc. So strong electrolytes are completely ionized in aqueous solution. Example, you can see HCl plus H2O gives H3O plus Cl minus. Similarly, you can take the case of NaOH on treatment with that of water, it gets dissociated into Na plus OH minus. And in general, the ionization of a weak electrolyte Ab is represented as follows. Ab plus aqueous reversible sign A plus B minus. And such an equilibrium is called as your ionic equilibrium between the ions and the undissociated electrolyte. When we apply the law of equilibrium, chemical equilibrium to it, we get A plus B, A plus molar concentration into B minus molar concentration upon AB is equal to Ki, which is called as ionization constant. Now let's see the difference between dissociation and ionization. When an ionic compound is dissolved in water, the ions which are already present in the solid compound separate out and the process is called dissociation. On the other hand, when a neutral molecule like HCl, which is a polar compound, covalent compound, which does not contain ions, but when dissolved in water, splits to produce ions in the solution. The process is called ionization. Generally, the two terms are used without any difference. Let's come to now Ostwald's dilution law, ionization of weak electrolytes. We'll consider the example of acetic acid dissolved in water. It partially gets dissociated into H plus and CH3COO minus ions and the following equilibrium is obtained. So CH3COOH plus H2O gives CH3COO minus plus H3O plus. When I apply the law of chemical equilibrium K, that is equal to molar concentration of CH3COO minus into molar concentration of H3O plus upon molar concentration of CH3COOH into molar concentration of H2O. In dilute solution, since H2O is taken constant as it is present in pure liquid state and the product of K and H2O constant is denoted as Ka, that is called as ionization constant or dissociation constant of an acid. So Ka equals to molar concentration of CH3COO minus into molar concentration of H3O plus upon molar concentration of CH3COOH. If C represents the initial concentration of the acid in moles per liter and alpha be the degree of dissociation, then equilibrium concentration of the ions is equal to C alpha for CH3COO minus and H3O plus, and that of the undissociated acetic acid equals to C into 1 minus alpha. So when I see into this equation, CH3COOH plus H2O gives CH3COO minus plus H3O plus. Initial concentration of CH3COOH is C moles per liter. Concentration at equilibrium, since 1 minus alpha, moles of it get dissociated. So remaining will be C into 1 minus alpha acetic acid, and formed CH3CO minus is C alpha, and H3O plus formed is also C alpha. So I can calculate the dissociation constant of an acid Ka by putting in this equation equals to C alpha into C alpha divided by C into 1 minus alpha. That is equal to C alpha square upon 1 minus alpha. That is equation 2. Now, in case of weak electrolytes, the value of alpha is very small, and so we can neglect in comparison to that of 1 minus alpha. We can take the value of it as 1. Hence, Ka equals to C alpha square, or alpha equals to root over Ka upon C. The degree of dissociation alpha can be calculated at a given temperature C if Ka is known. Further, if V is the volume of the solution in liters containing 1 mole of electrolyte, then C equals to 1 by V. Hence, we have alpha equals to root over Ka into V. And this is equation 4. Similarly, you can calculate for a weak base like ammonium hydroxide. We have alpha equals to root over Kb upon C, which is also equal to root over Kb into V. And the above equations lead to the following result. For a weak electrolyte, the degree of ionization is inversely proportional to the square root of molar concentration, or directly proportional to the square root of volume containing 1 mole of the solute, and this is called Ostwald's dilution law. The question comes in your exam, state Ostwald's dilution law. So this is the statement you'll be writing. Next, keep in mind the approximation 1 minus alpha is equal to 1 can be applied only if alpha is less than 5%. If on solving a problem by applying the approximate formula, alpha comes out to be greater than or equal to 5%, the problem may be solved by applying exact formula, and alpha may be calculated by applying solution of quadratic equation, that is alpha equals to minus b plus minus root over b square minus 4ac upon 2a. Ostwald's dilution law is applicable only to weak electrolytes, because for strong electrolytes, alpha is almost equal to 1. That is, Ka tends to infinity. Look at this problem and see the solution of it. Question is, calculate the degree of dissociation and concentration of H3O plus ions in 0.01 molar solution of formic acid. Ka given here is 2.1 into 10 raised to minus 4 at 298 Kelvin. So here you see formic acid HCOOH plus H2O gives H3O plus HCOO minus. This is the decomposition reaction that takes place when it is ionized in water. Let alpha be the degree of dissociation. Initial concentration of formic acid is given here as 0.01 molar. Concentration at equilibrium will be 0.01 into 1 minus alpha, and H3O plus and HCOO minus formed equals to 0.01 alpha respectively. Because alpha is very small and can be neglected in comparison to 1, Ka equals to 0.01 alpha into 0.01 alpha upon 0.01, 1 minus alpha. Here the value of alpha I take in the denominator portion, we take it as 1. So on calculation, we get alpha square equals to 2.1 into 10 raised to minus 2. And alpha is root over this value, which comes out to be 0.14. And thus I can calculate the concentration of H3O plus ions, that is equal to C alpha. So C here is 0.01 into alpha value, I got it as 0.14. That is equal to 1.4 into 10 raised to minus 3 moles per liter respectively. So we calculated degree of dissociation alpha value, as well as we also calculated the concentration of H3O plus ions. Next, I come to the next concept, and here it involves various concepts of acids and bases. The first concept of acids and bases, which you are all well aware with, is the classical concept of acids and bases there. So an acid, according to classical concept of acids and bases, an acid is substance whose aqueous solution possesses the following characteristic properties. First is it conducts electricity. Second, it reacts with active metals like zinc, magnesium, etc. to give hydrogen, and it turns blue litmus red. It has sour taste, and its acidic properties disappear on reaction with the base there. So this is the classical concept of an acid. Classical concept of a base is a substance whose aqueous solutions possess the following characteristic properties. It conducts electricity, turns red litmus blue, has a bitter taste, has a soapy touch, and whose basic properties are destroyed on reaction with an acid. So this is the classical concept of an acid and a base. The second concept is Arrhenius concept of acids and bases. So Arrhenius gave the definitions of acids and bases as follows. An acid is defined as a substance which contains hydrogen and which, when dissolved into water, gives H plus ions. Hydrogen ions are given out. Substances like HCl, HNO3 and H2SO4 contain hydrogen when dissolved in water, dissociate completely into H plus ions and the negative ions as follows. So you can see HCl on dissolution water produces H plus Cl minus, nitric acid, HNO3, H plus NO3 minus, H2SO4 gets dissociated into 2H plus SO4 2 minus. So such acids are called as strong acids. And substances like acetic acid, carbonic acid, phosphoric acid, etc., when dissolved in water, dissociate into ions to a very small extent. So you can see the case CH3COOH when dissolved in water gets dissociated, partially dissociated in CH3COO minus plus H plus. H2CO3 gets dissociated into 2H plus CO3 2 minus. Partial dissociation takes place. H3PO4 3H plus PO4 3 minus. Dissociation takes place to a very small extent, and such acids are called as weak acids. So in general, you can write HA, which is a weak acid, gets dissociated into H plus A minus. All the properties of an acid are due to the H plus ions which it furnishes in aqueous solutions. Then let's come to the Arrhenius base. A base is defined as a substance which contains hydroxyl groups and which, when dissolved in water, gives hydroxide ions. Substances like sodium hydroxide, potassium hydroxide containing OH groups, when dissolved in water, dissociate completely to give OH minus ions, and they are called as strong bases. NaOH, when dissolved in water, gets dissociated into its respective ions Na plus OH minus. Similarly, KOH gets dissociated into K plus OH minus. So they are called as strong bases. Whereas substances like ammonium hydroxide, calcium hydroxide, magnesium hydroxide, aluminum hydroxide, etc., they dissociate to very small extent as shown. NH4OH, when dissolved in water, gets dissociated into its ammonium ion NH4 plus OH minus. So that's why they are called as weak bases. So this is the Arrhenius concept. And when an acid and a base are mixed together, they react to form salt and water, and the reaction is called as neutralization reaction. So you can see the example. Sodium hydroxide reacts with HCl. Sodium hydroxide is a base reacting with HCl acid, and it results in the formation of salt plus water, NaCl plus H2O is formed. So according to Arrhenius, neutralization may be defined as the process in which hydrogen ions given by the acid and the hydroxide ions given by the base combine to form unionized molecules of water. The third concept is Bronsted-Lowry concept of acids and bases. So according to Bronsted and Lowry, an acid is defined as a substance which has the tendency to give a proton. That is, an acid is a proton donor, and a base is defined as a substance which has a tendency to accept a proton. That is, a base is a proton acceptor. The above definition is explained with the following examples. You can see HCl plus H2O gives H3O plus Cl minus. So HCl here you see is acting as your Bronsted acid because it is donating its proton and it is going to Cl minus state by giving a proton, and H2O is accepting H plus and forms H3O plus. Similarly, you take another example, CH3COOH plus H2O gives H3O plus CH3COO minus. NH3 plus H2O gives NH4 plus OH minus. CO3 2 minus plus H2O gives HCO3 minus plus OH minus. HCl plus NH3 gives NH4 plus Cl minus. So here you see NH3 has accepted H plus. So this NH3 is acting as your Bronsted base. So the following results may be derived from these equations. HCl and CH3COH are acids because they donate a proton to H2O. NH3 and carbonate ion are bases because they accept a proton from water. Not only molecules, but even the ions can act as acids or bases. Example, carbonate ion is acting as a base in the above example. In the first two reactions, water is accepting a proton and hence is base. In the next two reactions, water is donating a proton and hence is acting as an acid. Thus, water acts both as an acid as well as a base and is called amphoteric in nature. The reaction E above indicates that Bronsted-Lowry definitions of an acids and bases are not restricted to aqueous solutions. In this reaction, HCl is acid because it gives a proton and NH3 is a base because it accepts the proton. The presence of hydroxyl groups is not essential for a substance to act as a base. The only requirement is that it should have a tendency to accept a proton. The above reactions indicate that substance acts as an acid, that is, it gives a proton only when another substance to accept the proton, that is, a base is present. For example, acetic acid does not act as an acid in benzene solution because the latter does not accept the proton. The reverse reactions are also acid-base reactions. For example, in reaction A, in the reverse process, H3O plus can give a proton and hence an acid, while Cl minus can accept the proton and hence is a base. Thus, there are two acid-base pairs in a reaction A. These are HCl, Cl minus and H3O plus H2O. And these acid-base pairs are called conjugate acid-base pairs. A conjugate pair of acid and a base differs by a proton only. That is, conjugate acid gives conjugate base plus H plus. So it differs only by a proton. Now look at the examples here. HCl plus H2O. HCl acts here as your Bronsted acid and H2O acts as your Bronsted base. So HCl will result in the formation of conjugate base Cl minus, and H2O will result in the formation of conjugate acid, that is H3O plus. Similarly, you can take the example of CH3COOH plus H2O gives H3O plus plus CH3COO minus. H2O plus NH3 gives NH4 plus plus OH minus. H2O plus CO3 2 minus gives HCO3 minus plus OH minus. HCl plus NH3 gives NH4 plus plus Cl minus. So if it acts as a Bronsted acid, it will result in the formation of its conjugate base, and if it acts as a Bronsted base, it results in the formation of its conjugate acid. That is the concept of Bronsted-Lowry acids and bases. Now look at the question. The question is, what will be the conjugate base for the following Bronsted acids? HF. So conjugate base will be F minus. H2SO4. Conjugate base will be HSO4 minus. So conjugate base actually is equal to Bronsted acid minus H plus. So here HCO3 minus, remove one H plus, it forms CO3 2 minus respectively. Similarly, could look at the next question. The question is, write the conjugate acids for the following Bronsted bases. So conjugate acid is equal to Bronsted base plus H plus. So NH2 minus, the conjugate acid for it is NH3. NH3, the conjugate acid for it is NH4 plus. HCOO minus, conjugate acid is HCOOH respectively. Hope you have followed. Let us come to the last concept of acids and bases, and the fourth concept of acids and bases is Lewis concept of acids and bases. So an acid is defined as a substance which is capable of accepting a pair of electrons according to Lewis acid. This is electronic concept. And a base is defined as a substance which is capable of donating an unshared pair of electrons. In other words, an acid is an electron pair acceptor, while a base is an electron pair donor. So keep in mind about Lewis acid and Lewis base. Lewis acids are electron pair acceptor, while a base is an electron pair donor. Now, types of Lewis bases. They are of two types. One is neutral molecules like NH3, RNH2, ROH, H2O, etc., in which one of the atoms has got at least one lone pair of electrons. And the second type is all negative ions like F minus, Cl minus, Br minus, I minus, OH minus, Cn minus, etc., will act as your Lewis base. Let's look into the types of Lewis acids. Lewis acids are of four types. One is molecules having a central atom with incomplete octet. Example, BF3, AlCl3, FeCl3. Hence, central metal atom can accept a pair of electrons. Example, AlCl3 plus Cl minus gives AlCl4 minus. Second category is simple cations, silver ion, copper ion, iron ion, etc. These ions can accept pairs of electrons and hence they can act as Lewis acids. The third category is molecules having central atoms with empty d orbitals. Central atoms in these molecules can expand their outer octet by taking up electrons in their empty d orbitals. So examples you can take SiF6 2 minus, SiF4, it acts as a Lewis acid. On treatment with Lewis base, 2F minus gives SiF6 2 minus. So examples are SnCl4, SiF4, PF5, etc. Having central atoms containing empty d orbitals, they can act as Lewis acids. And the last category is molecules containing a multiple bond between two atoms of different electronegativities. Example, you can take the case carbon dioxide contains double bonds between carbon and oxygen. Since oxygen is more electronegative than carbon, therefore carbon acquires a slight positive charge and thus can accept a pair of electrons. Hence, carbon dioxide acts as a Lewis acid. So it reacts with a Lewis base and it forms a bicarbonate ion. CO2 plus OH minus gives HCO3 minus. So molecules containing multiple bond between two atoms of different electronegativities can also act as Lewis acid. So carbon dioxide will act as a Lewis acid. Now look at this question. The question is, classify the following species into Lewis acids and Lewis bases and show how these act as such. So as I said, negative charges OH minus, F minus, or those that are having lone pair of electrons on them, they can act as your Lewis bases. So OH minus is a Lewis base as it can donate an electron pair. F minus is also a Lewis base because it has 4 lone pairs of electrons and can donate any one of these. H plus and BCl3 act as Lewis acid. H plus is electron deficient. It can accept electron pair from bases like OH minus, F minus, etc. That's why H plus acts as Lewis acid. BCl3 is a Lewis acid as boron is electron deficient in nature, as it has only 6 electrons instead of complete octet. Hence, it can accept an electron pair from species like ammonia, amines, etc. So keep in mind, Lewis acids are electron deficient in nature, and Lewis bases, they are having uh, in their electron, they can donate an electron pair. Donors, they are electron donors. So because of the presence of either negative charge on them, or they are having at least one lone pair of electrons on them, they come under Lewis bases. Electron deficient Lewis acids. So I repeat, OH minus, F minus will act as Lewis acids. H plus and BCl3, OH minus and F minus acts as Lewis bases, and H plus and BCl3 acts as Lewis acid. So hope it's all clear. Thank you, children. In the next class, we'll be dealing about that of ionization of acids and bases in detail. Till then, have a nice day.